Hi guys, we're going to take a look at predicting and calculating entropy. At this point, you've had an introduction to what entropy is through the online simulation and interactive we did. And now we're going to look at how we predict what's happening with entropy, if it's increasing or decreasing, and how we actually calculate values. So how do we predict if entropy is increasing or decreasing? So to determine if it's increasing or decreasing, we will look at the number of possible arrangements the particles can be in. As you saw, entropy is really a measure of how many arrangements the particles and the energy can be in. So the more arrangements possible, the more entropy there is. So this may mean thinking about states of matter, the amount of energy change, or how the chemicals change within a chemical reaction. We will explain how to predict these changes and how we can calculate the entropy of a standard system. Any increase in the number of arrangements, or what we call microstates of a system, will result in an increase in entropy. Two notable changes that will cause an increase in entropy are an increase in temperature, because our particles are moving faster. They have a faster average kinetic energy, so that means that they're going to be able to occupy more arrangements and more microstates, so they would have an increase in entropy, or an increase in the volume, or the space the particles take up. Now, this is not necessarily an increase in the number of particles, which sometimes we get confused for volume, but how much space they take up. So, for instance, having particles in a small 10-liter container versus gas particles in a larger 20-liter container. There's more space to take up, so they would have more entropy. They're spreading out more microstates and arrangements. So we're going to try doing some predictions here. The first one's done for us. So we're going to look at how enthalpy change and entropy change are related. So enthalpy is that change in energy of our system. So we can think about, is it taking in that energy, is it endothermic, or is it giving it off exothermic? And that does, in terms of state changes, give us an idea of what's happening with the entropy as well. So our first one, evaporation. So taking something and going from a liquid to a gas, it would have to take in extra energy. So it's a positive value to go from a liquid to a gas, and it would have to that means it would increase its entropy because the particles are spreading out more, turning into a gas, and they're taking in that extra energy. So we're going to have more microstates. Condensation is a release in energy. We're going from liquid or from gas back into a liquid, so it has to give off its extra energy. So our delta H would be negative. And in that case, because we're condensing it, we're bringing those particles closer together, we're decreasing how much space they're in, their volume, then we would have a negative sign for our entropy because we're going from gas to liquid. Sublimation is the state change where we go straight from solid to a gas. So that's what happens when dry ice, which is solid carbon dioxide, is exposed to warmer temperatures. It jumps straight from being a solid to a gas. So just like evaporation or things like that, it has to take in energy to go from that solid to gas phase. And so those particles going from the solid to the gas are spreading out, occupying more volume. So we're going to have a positive delta S value. Deposition is the opposite of that. So if we could like take carbon dioxide gas and force it into its solid form and make that dry ice, then we would have to release its extra energy. We have to slow down those particles, take out their extra energy, and so that would be a negative. That's a release of their energy, which means also we're taking that gas and forming it in solid. It's going to take up less volume, so then we would have a negative sign change for delta S. So we're just seeing like what's happening with the energy and what's happening with that volume and that energy in terms of delta S. Last two, maybe try these two, pause the video, and then check them, make sure you're on the right track. All right, so let's check them. So melting. Melting means we're going from our solid phase to our liquid phase. We're going to have to add energy to make that happen, which means we're also going to increase the motion of the particles. They're going to be able to occupy more arrangements in that. So we're going to be positive in our delta S. Freezing, we're going to have to take our liquid and turn it into a solid. So we're going to have to release its extra energy, be negative, and the particles are getting locked into place. So we're forming those intermolecular forces more. So they're going to have less arrangements possible. So we're going to have a negative delta S. So in terms of these, we really want to think about in delta S, what's happening with the arrangement of the particles. Can they occupy more different arrangements, and is there more disorder to it? Or are they occupying less arrangements, less volume, and they're becoming more kind of ordered and organized? So dissolving and dissociation. When an ionic compound like potassium chloride is dissolved in water and the ions dissociate or separate, a mixture of water and ions replaces the pure solid in pure water. So we've got the ionic compounds separating into their ions and mixing in with the water. The ions move within a larger volume and they're not locked into place as they were in the solid. So they will experience an increase in entropy. They're more spread out, so they get an increase in entropy. However, some of our water molecules now become attracted to the ions and are now water of hydration. So we've drawn this before, but we'd have our ion, say our positive ion, so from the potassium, okay? And then we'd have our water where we'd have the oxygen and then it's two hydrogens attached. The oxygen, because it's more electronegative, it's going to attract to the positive ion, and the water molecules would surround that ion. We've drawn this before, we've looked at this before, especially when we talked about intermolecular forces. We have something polar, something ionic, we get an ion dipole force forming between these. So that kind of makes our water molecules, because we're creating those intermolecular forces, they're going to be more locked into place. They can be knocked off and other water molecules can replace it, but because they're creating those stronger attractions, they aren't moving around the solution as freely. So they experience a decrease in their entropy, the decrease in their possible positions. So what happens then? Since this is all in the same solution, we would have to find the total entropy. An overall increase in entropy when dissolving a solid is usually the dominant force. So because there's so much of the ionic compound spreading out within the solution, we're going to have more of an increase in entropy than we would have that little decrease because of the water surrounding the ions. So when most salts dissolve, we can predict that they would have an increase in entropy. So we've looked at some state changes, and now we've looked at dissolving things. And our next stop is chemical reactions. So in a chemical reaction, when they occur, we can analyze it in a similar way to other situations. So in this reaction, we can see that when the products are formed, the NO2, there are new nitrogen-oxygen bonds that we've made. So we can see we've already had one nitrogen-oxygen bond, so we'd be creating like one here and one here to get that second bond of our atoms. The decrease in the number of total molecules, so we went from 3 total molecules in the reactants to 2 in the products, and the decrease in their ability for motion because they're now bonded, gives fewer microstates or arrangements, so they don't have as many places they can arrange themselves as. Therefore, they have a decrease in entropy of our system. So that's one thing we can analyze, is how many chemicals we're starting with, how are they bonding, and that can help us look at the increase or decrease in the entropy. So in this case, we went from 3 moles of reactants to only 2 moles of products that are all gases. So we're going to decrease how many particles we have. That means we're going to decrease our entropy. So we would expect the entropy of a system to increase. So we're going to have more arrangements for these following processes. So this can help us make more predictions. When gases form in a reaction from either solids or liquids, so we're creating a gas from solids or liquids. When liquids or aqueous solutions form from solids, we're dissolving something, we're melting it, or we're reacting it to form liquids from a solid. Or the number of total gas molecules increases during a chemical reaction. So if we can look at our coefficients, our moles, and we can total the moles on the reactant side and the product side, and if that number increases going to the products, we have an increase in entropy. So now we're going to practice making some predictions. It would be a really good idea to pause the video now, try them out on your own, and then come back and check them. So hopefully if you've tried these out and we can check through them. So our first situation, we've got water forming. Water is a liquid forming a gas, so that would increase its arrangements. That would be a positive change in entropy. Excuse me. Part B, we're going from having dissolved ions to creating that solid and taking away that aqueous solution. We're taking away the water, so that would be a decrease in entropy. We're making that solid, we're taking those ions that were spread out and putting them together, so that's less arrangements. All right, part C, we're taking a solid and a gas, and that we're forming that into a solid. We're creating more bonds, so we're locking more atoms in place. That's going to decrease our entropy. Part D, we're taking 2 moles of gas on the left, so 1 nitrogen, 1 oxygen, and creating 2 moles of gas on the right. So this is one where we can say that it's approximately 0, or it's going to be pretty close to 0, because we can't predict just based on looking at it without values what's happening here, because we're going from gas to gas, we're going from 2 moles to 2 moles, there's no other extra information that really helps us. All right, part E, we've got a solid and a gas forming a solid, so we're taking that gas and it's becoming part of the solid, we're locking those particles in place, less arrangements, that would be negative. Part F, we're taking a solid and creating 2 gases from it. So that one, we're spreading the particles out, we're reacting and separating them into 2 separate molecules instead of 1. So we're going to have a positive, more arrangements. Part G, we've got gases across the board. So we've got 2 moles of gas in the SO2, 1 mole of gas in the oxygen. So that's 3 total moles of reactants. We're forming 2 in the product. So we're decreasing our amount of product or amount of moles, more particles, so that's going to be less arrangement, so that should be a negative. And our last one, we're going from solid carbon dioxide to gaseous carbon dioxide. That's that sublimation that we talked about earlier, where this is going dry ice forming from the solid to the gas, so that's positive. So we can see how some of the states of matter changes can be written as a reaction in A and H, and then how we can predict this for some reactions. Now we're going to take a look at calculating our delta S of our reaction. So what is this? The entropy change, delta S, in a chemical reaction can be calculated using delta S naught values. So these are the standard molar entropy values. Okay, so standard because of the little circle, the naught symbol. And molar entropy is the delta S. So S is what represents entropy. I think S is used because it ran out of value, or ran out of letters by now when they came up with entropy. Other than that, the letter doesn't match the name, unfortunately. The units for this are reported in joules per mole Kelvin. So we can see that it's in joules, which is a little different. We've been using kilojoules a lot. And it's not just per mole, it's per mole times Kelvin. So the temperature does play a role here. When we increase temperature, it's going to change things. So the value of the entropy change with temperature, the value of the entropy changes with temperature as shown in those units. So the only chemicals that would have 0 entropy because the temperature is involved would be a pure crystalline solid at absolute 0. When it's perfectly 0, there would be no motion in the particles, and therefore only a single microstate or arrangement would occur. That would allow something to have an entropy of 0. We've never gotten there. They've come really close to creating absolute 0, but not gotten there yet. So we don't have anything with a delta S of 0. So all chemicals will have a positive entropy, and they are measured at 298 Kelvin. So in this table to the right, you can see a lot of values there. They're all measured at 298 Kelvin as shown in the top of the table, and they're all positive. So as we increase temperature, we get more and more entropy, so the numbers would go up. So we had to measure in a standard way. We had to pick a temperature because temperature would change these values. So they said, okay, 298 Kelvin, which is 25 degrees Celsius room temperature. So that's where all of these values come from. Now, if we want to calculate delta S, we need an equation. But before we get there, we're going to notice some of the things going on with these numbers. So first, we can notice that some of the values of gases are greater than those of liquids or solids. So our gases are towards the top, liquids in the middle, solids at the bottom. We can see we get our largest numbers up at the top. So as we have faster moving particles, they're going to be more dispersed or spread out, have more arrangements. They're going to have higher entropy. The S values are generally increased with increasing molar mass. So we could see that, for instance, with the first three chemicals, hydrogen, nitrogen, oxygen. Those are in order of their molar mass, hydrogen being the smallest. And as we have more molar mass, we have an increase in their entropy. So that's another way to look at entropy of chemicals if we're comparing two. And then the values generally increase with an increased number of atoms in the formula. So when we have more atoms, we've got more arrangements possible of them because some molecules can kind of arrange themselves in multiple ways. So we get more entropy in those substances. So these values, where do they come from? Tables like this and the one that you have in the back of your book. We used it for the delta H values already, so this is actually going to be the last column in that same table. All right, so how do we solve it? This calculation is done the same exact way, actually, as the calculation for delta H when we use the standard enthalpies of formation, so using that same table in the back of our book. So when we were doing those calculations, for delta H, we actually learned how to do delta S calculations. We're just plugging in different numbers. The equation on the equation sheet is also written the same way. So our delta S is equal to the sum of the delta S for the products minus the sum of the reactants. Same idea. So let's see this. An example, so calculate the change in standard entropy of the system for the synthesis of ammonia from nitrogen and hydrogen gas. So we can see we have nitrogen plus hydrogen forming ammonia. So let's look at this first. Let's predict if it might be negative or positive. So we've got 1 mole of nitrogen, 3 moles of hydrogen. That gives us a total of 4 moles of gas on the left. And then we only have 2 moles of gas on the right. So we're putting those particles together, creating more bonds, reducing the number of total particles. So we have less arrangements. So it should be a prediction of negative. So now we're going to plug into our equation. So again, we want products minus reactants. So we'd have our delta S of our reaction equals to 2 times the NH3, because it has a coefficient of 2, minus the reactant, so minus N2, plus 3 of the hydrogen. Now we're going to replace the chemicals with the values from the table. So you've got the little table on your notes page. It has the same values in it. So 2 times our 192.5 for the NH3. We got 191.5 for the nitrogen. And 3 times our 130.6 for the hydrogen. So we can plug those in. And then from there, we would want to simplify. So our 2 times our 192 gives us 385.0. Simplifying the right side, we get 391.8 for our last term. And then we can go ahead and calculate our final answer in our calculator. So make sure you try this out. Make sure you can get the same answer, negative 198.3. We've got a decimal in all our values, so we want to keep one in our answer. And our units all stay the same, joules per mole Kelvin for our delta S of our reaction. Okay. So pretty straightforward, same as delta H calculation. All right, so we're going to do the second example. We want to calculate the standard molar entropy of carbon dioxide, CO2, from the following information. So we're given a combustion reaction, C6H6, which is called benzene, plus oxygen making carbon dioxide and water. So from the table that you have on your note sheet from the previous slides, we have available the values for the C6H6, the oxygen, and the water. We're going to go ahead and calculate the value for carbon dioxide, and we're given the delta S value for the entire reaction. So that would be like what we calculated in the previous one. So we're looking for that missing piece. So again, we want to set up our equation. We'd have our delta S equal to our products minus our reactants. So 12 carbon dioxide plus 6 water is our products, minus the 2 benzene plus 15 oxygen as our reactants. And then we want to replace our values, or our symbols, with their values. So on the left side, we would have that 82.6. And then on the right side, we're going to leave our carbon dioxide. We aren't sure what that is yet. We're solving for it. We have 6 times 188.8 for water. And then we're subtracting the other term, so 2 times 269.2 for the C6H6, and then 15 times 205.0 for the oxygen. Now we want to simplify our equation down. So first thing we can do is simplify some of the multiplication and addition that we have. So the 6 times 188, we can multiply that out. And then in the other brackets, we can multiply and add and kind of simplify things down. So make sure you're checking these in your calculator, that you're getting the same numbers, and you're able to do those calculations. The next part would be to simplify the right side even further. So we've got the 1132.8 minus 3613.4. So we can go ahead and subtract those two terms. So we've got our 12 carbon dioxide on the right minus 2480.6. That's those two terms simplified. So now we can start dealing with the right or the left side of our equation too. So to simplify this, the next step would be to add the 2480 to the other side of the reaction, or of the equation, excuse me. And we get 2563.2. We get a positive value there, joules per mole Kelvin, and that's equal to our 12 carbon dioxide. Now we want to get rid of that 12, so we're going to divide both sides by 12, and we get 213.6 equal to our entropy for carbon dioxide. And we could confirm this value by looking it up in the table in the back of your book on page, I believe it's 1059. Off the top of my head, same table as our delta H values that we've done before. So we could use that to confirm our value. So that's another way we can use this equation, is to solve for one of the missing pieces. We're pretty used to using this with our delta H's, so it's just some more practice on the same type of equation, and we're actually going to have a third one that uses this same format. So it's pretty helpful, it gets you lots of practice on it. So we're going to do the practice next in class.